you very much, and thanks the organizers for organizing and inviting me. I'll be talking about Quench Dynamics. Here are the characters who did the work, Colin, Deepak, and Gary. And what I'll talk about is Quench Dynamics, namely how a system evolves from some initial state under the influence of a Hamiltonian. So, non-equilibrium, new frontier, all the new questions, doesn't need introduction. I will talk about the system that is pictured here on the left, namely a system that is modeled by the Lieb-Liniger model, which I'm going to introduce in a minute. So one starts from a state that is initially defined by a lattice, and then one removes the lattice. This is the initial state, which then evolves under the influence of a Hamiltonian with interaction. There are other ways. So here it's the Lieb-Liniger Hamiltonian. All we have is interaction among the particles, but they move in a flat space. Another piece of work that I will not talk about is when you start from some initial state and just lower the barriers. Now you go from a mod state to a superfluid. And here are the experiments that were done in 2 dimensions where, where initially the system was given here in a superfluid, then so it's the opposite way than I depicted here. And the system evolves, moves to a mod, and because it's finite size, it moves back to a superfluid. So the Quench protocol consists of starting with an isolated system with some given time-dependent Hamiltonian that may be depending some work parameter, some initial state, which may be the ground state of some Hamiltonian, which I'll call HA at this point. And the work function could be arbitrary, and one wants to understand how a system evolves in time under the effect of this Hamiltonian. This is, I will simplify the problem for a quantum quench. One prepares the system at point A and evolves it with a constant Hamiltonian subsequently. So the process depends on the Hamiltonian, of course, but also on the initial state. So both of them define the evolution. And one can characterize it by local characteristics. How does a local observable change in time under the influence of the Hamiltonian? How do the correlations? How does thermalization? And so on and so forth. And there are also global characteristics like quantum works or spread of entanglement. So the question is, how does one evolve the initial Hamiltonian? Of course, there are several methods, but setting up the problem is simple. Suppose I'm given some phi naught initially, and I can expand it then in using the partition of the unity of the eigenstates of the propagating Hamiltonian. Let me call those F lambda. Then I can express the initial state in the basis F lambda. And then formally, it's very easy. One applies the evolution Hamiltonian to this state. It acts on those basis states, picks up, I think I'm missing a t there, E minus I epsilon lambda t, and this is a formal expression. Now, many Hamiltonians in 1 dimension turn out to be integrable, which when they are integrable, you can construct the eigenstates via what is called the Bethe-Ansatz. So once you know those states, you can imagine how to evolve the Hamiltonian and compute the subsequent evolution. But the Bethe-Ansatz is an old technique going back to Bethe in the early 30s and has been used very efficiently to carry out thermodynamic calculation. Typically what one does, one imposes periodic boundary conditions, or more recently open boundary conditions. One obtains equations which are called the Bethe-Ansatz equation, from which one obtains the spectrum and then the thermodynamics. But when you want to do non-equilibrium, there are additional difficulties. In particular, you see you have to be able to calculate these quantities, these overlaps or form factors, and reconstruct the whole system from it. So there is a lot of work that was done in this direction, particularly a very nice work on quench action by Koh, Essler, and others. What I want to present is an alternative approach, a contour approach, which does not require computing overlaps and allows you to calculate the time evolution. Of course, as it has its own problems. Okay, so again, instead of having the expansion into form factors, I will argue, following Vladimir Yutzen, that one can provide a contour representation of the initial state. In other words, if you are sharp, there is a mistake here. I'm sorry. This should be not a this should be not a bra, but a parenthesis. So you can expand the Hamiltonian by introducing the following expression. Instead of carrying out the standard partition of the unity, you can introduce an expansion in terms of Yutzen states, F lambda with a parenthesis. These are obtained from the typical Bethe-Ansatz eigenstate by setting the S matrix which characterize such eigenstates by 1. In other words, by non-interacting states, which allows computation in a very easy way of these overlaps. And one has to do it in one quadrant. For example, if you are talking about boson, one quadrant where the particles are ordered will allow you to reconstruct the wave function everywhere. The price that you have to pay for this simplification is that you have to choose a contour in momentum space, lambda being, let's say, momentum variables, and these are determined by the pole structure of the S matrix. I will illustrate the idea in a minute. So if we are talking about the system in an infinite volume, the momenta remain unquantized, and then all you have to do is integrate over the momenta over those contours. And having achieved that, then you have a very easy time in calculating the time evolution. So let me illustrate this by thinking about the Lieb-Liniger model, which describes ultra-cold atoms. The potential, the interaction between them is short range, and the Hamiltonian describes particles moving on a line with short range interaction, and this can be realized in the lab very nicely. For example, this is taken from a review by Bloch et al., which is obtained by crossing lasers, creating a one-dimensional potential hole. So this system, this Hamiltonian describes atoms on the line. These are neutron atoms. The interaction is short range, and this description is valid if the density is sufficiently low so that you can describe them this way. So here are the eigenstates of the Hamiltonian given by, obtained first by Lieb and Liniger. So the wave function, f of lambda, is characterized by, for n particles, is characterized by momenta lambda 1 to lambda n. And the eigenstate is given by a wave function multiplying a creation operator B dagger, n of them for n particles, with the wave function characterized by a dynamic factor. So you see, this is a signum function. If yi is less than yj, this factor is 1. If yi is larger than yj, it's 1. If yi is less than yj, then we get lambda I minus lambda j plus ic, lambda I minus lambda j minus ic, which is a phase. This is the S matrix I was referring to. C, the coupling constant, can be positive or negative and can be controlled in situ by a Feshbach resonance. And notice that the S matrix has poles. These poles determine what trajectories we have to integrate over. So this is a full-fledged eigenstate of the Hamiltonian. You apply the quantum Hamiltonian to this eigenstate, and the eigenvalue is given by sum over the momentum squares of the particles. And as I said, one can impose then boundary conditions which lead to equations on the allowed momenta lambda 1 to lambda n. Solving these equations then gives you the energy eigenvalues. Now, we are interested in the dynamics. So in the infinite volume limit, the momenta are unconstrained. So all we have to do is integrate over there. Later on, I'll talk about what to do if you are talking about finite volume. So the contour representation, F naught, given in terms of the Utzon states, is the following. Here is F naught. Given some arbitrary initial state phi naught, we can represent it now in terms of the basis of eigenstates of the Lieb-Liniger model. So here is the initial state. This tells me that I'm in the first quadrant. This is the wave function of the eigenstates that I introduced before, and this is the overlap phi naught with F lambda. Notice how simple it is. It's so simple because I'm using the Utzon representation. Now, I have to choose the contour so as to make this indeed a mathematical identity. And that depends on the sign of the coupling. If the coupling constant is positive, namely we have a repulsive interaction, then all the momenta are real and integrated over the line. If the coupling constant is negative, then you have to space them out by an amount larger than C, than absolute value of C. Now, the proof of this is actually very straightforward and requires just Cauchy theorem and closing the contours and capturing poles of the S matrix. And then you can show easily that indeed this is a correct mathematical identity. So given this, I can now time evolve. All I need to do is to add the time evolution factor, e to the minus I lambda j squared t. This is the energy. And now I have a dynamic time evolved wave function valid for any time. What do I do with it? I have to calculate, and I'll calculate some quantities that are of interest. So I will ask the question, how does the density evolve in time, and how does the noise correlation evolve in time? So let me start, let's say, with two particles localized next to each other. Here is the initial state, and then I can do the integrals and I find that the time evolution wave function is given by this expression, the original phi naught integrated with the evolution factor, and when you do the integral, you get the error, complementary error function here. So the dynamics depends on whether the two Gaussians are close or remote from each other. If A, let's say the initial distance between them is larger than sigma, sigma characterizing the Gaussians, then essentially there is no effect. What we have here is the effect of a natural broadening of a Gaussian with time, as opposed to the interaction when the two wave functions begin to overlap. So if they are sufficiently far, the overlap is going to be so minimal that you are not going to see any effect. And I measure what's happening exactly in between. On the other hand, when the initial condition is such that they are sufficiently close to each other, you can see the effect of interaction. So the blue line is non-interacting, the red line is repulsion, the green line is attraction, and you see that depending on repulsion or attraction, the density is going to increase or decrease. A more interesting effect is the Hanbury-Brown twist effect. So what is the Hanbury-Brown? This is taken from Wikipedia. They were astronomers and they wanted to understand the correlation of light between two stars, A and B, as measured by two telescopes, capital A and capital B. And they showed that for free boson, the correlation is given by cosine, the x being the distance between A and B, while if they were free fermions, it's minus cosine x. And that is because it's constructive or destructive interference of the correlated light coming from the two stars. The correlation being here, and they correlate the beams coming from both sides. Here we have again, this is taken from Bloch and al. We have a Brown twist effect of two bosons. Let's say I put them next to each other, allow them to evolve and interact, and then I get a Hanbury-Brown twist effect. It's a time-dependent Hanbury-Brown, because unlike the stars that emit a constant, that are constant source of photons, here we have just a boson at the one time and allow it to evolve. Also, the bosons interact, and we can talk about many bosons and so on and so forth. So what I want to show is that if I have repulsive bosons, if they repulse each other, then as time evolves, the interaction between the bosons will always flow to infinity. We call this a dynamical fermionization. They behave like hardcore bosons or fermions. While if we have attractive bosons, they condense. So again, if I start with two bosons next to each other and calculate the noise correlation defined here, in the long time limit, if you do saddle point approximation, you find that it does not depend on x1 and x2 and t, but rather on two variables, psi x over 2t. So I'll have psi1, psi2 normalized by their value, psi1 expectation value, psi2 expectation value, and -1 is just for convenience. And so you see that if I have no interaction, I am going to get the cosine that Hanbury, Brown, and Twist were talking about. On the other hand, if I turn on an interaction, you see that as time evolves, it will turn over and become a minus cosine. And it does that for any value of c. If C is large, they turn over faster. If C is small, they are turned over later. And that is the minus cosine t, namely the destructive interaction, indicating that for a long, the variable is psi x over 2t, so it goes like 1 over t. Long time is here. So in the long time, we see that the repulsive bosons turn on to behave as fermions. You can do it for any numbers, 3, 5. You see here, this part of the plot describes the initial state, but what is here universal is the turnover, namely you get the anti-peak everywhere. As compared to attractive boson, which are going to condense into a bound states which will dominate the long time evolution. You can start, of course, with other initial states. Suppose you have some featureless initial state, some kind of an condensate. Again, you get this universal feature of a coupling becoming very, very strong as time evolves. And the argument that underlies this dynamical fermionization is actually straightforward. Phi naught of t is given by this expression that I have described before. And notice that where time appears is here. So let me do change of variable. Let me define lambda times square root of t as the new lambda. So it disappears here, but then it has to appear here. And you get a square root multiply, so you get lambda I over square root of t, lambda j over square root of t. Change variables, you multiply, you get the square root of t appearing here. When you send it to infinity, you see that this function becomes the sine function. So you get an expression where the sine function of yi minus yj multiplies the product of boson operators, and this is a famous Girardot transformation, which allows you to describe this product of sine functions and boson operators as a product of fermion operators, multiplied by the initial state that we started with. So they evolve as time goes on. As t dominates this evolution, they turn into fermions. So this argument is valid for any initial state. It just depends on the structure of the S matrix. And it was recently observed experimentally by the Weiss group. And the scaling argument fails for attractive bosons. Remember, the attractive bosons, you have to integrate over the contours which consist of lines which are parallel, and they are separated by an amount of c, and then this argument fails. So what we conclude is that the coupling constant effectively evolves with time. One can imagine that time plays the role as a cutoff that one reduces. The time evolution is like a RG in time. So you start at this point and you flow to infinity. You start at this point, you flow to minus infinity. And this language allows you also to argue that Hamiltonians that are sufficiently close, sort of they are in the basin of attraction of the RG in time, are going to behave in a similar way. And indeed, we did with Deepak a numerical, we put it on a lattice, we did the same calculation, and you can see the difference between, for two bosons, how they evolve in time. For C, equals to 0, they evolve one way. And if C is positive, you see they repulse each other and there's nothing here on the diagonal. So this time evolution is not just due to integrability. Integrability is an ingredient that allows you to calculate it, but the effect is really universal. And it was also observed experimentally by the Greiner group in 15, and you can see the two, you see the behavior here and here are very similar. So another example where one can use, where such an interesting behavior would occur, imagine space being filled with bosons, half the space from 0 to minus infinity. The initial state is made out of an array of Gaussians, and the right-hand side is empty. What will happen now if I allow the system to evolve? So, of course, you see there will be broadening of the Gaussians, and the bosons will start flowing to the right. So what happens here is some very interesting phenomena. If you allow the system to evolve sufficiently for a long time, it will evolve into a NES. NES means non-equilibrium steady state. So you can look at this picture here. Initially, we were, the red is the initial state where I had a constant density of bosons. And now let me pick a point x naught and study what happens as it evolves in time. So initially, of course, the density that I will measure will be 0. The bosons have not arrived. Then as time evolved, I will have a crossover regime, which is a little bit complicated, but we can nicely calculate it. But later on, as time goes on, notice that what I'm going to obtain a density that is independent of time and space. It's a constant, that is a characteristic of NES. But remnants of non-equilibrium are easily, oops. Oh. You see, the effect of non-equilibrium can be seen here. If we were in equilibrium, namely in finite volume, then of course we know the system was half filled, and then in the long time limit, the density would go from 1 over L, would end up, instead of being 1 over L here, it would be half 1 over 2L. But because there is always somewhere, since the system is infinite, there is always somewhere to expand into. Therefore, we have a reduction of the density by an amount of 1 over CL. This is an expansion in large C. And the system, the fact that the system is out of equilibrium can be measured even if we are in a steady state. Okay. What I wanted to talk about was about quantum work and Loschmidt amplitude, but okay, so I just say what I wanted to talk about. So I wanted to talk about, to define what quantum work is. Quantum work is a way of defining how much energy you put into the system when you quench it. And work turns out to be a random variable because you have to do two measurements. You have to start from your initial state, and then when you carry out the measurement in the final state, you could end up at any eigenvalues, and you calculate the overlap with initial and final, and then you obtain that there is a work distribution which is written out here, and which you can calculate more conveniently by what is called a Loschmidt amplitude. The Loschmidt amplitude being the amplitude of the overlap of the evolved state with the initial state. So it has many other names, return probability, survival probability, and having the Loschmidt echo, you can obtain the work distribution by just Fourier transform. And this is also related to many other concepts like dynamical phase transition. If you evolve the system and let it explore the full Hilbert space, then in time it may show singularities in the limit of the system goes to infinity. Singularities that would depend on the initial state as well as on the Hamiltonian, and they have been indeed measured experimentally by looking at some Eigen model material. Okay, so having again, I would explain how to carry out on a linear model such an evolution, which allows me to compute very nicely in the Loschmidt amplitude by the Hudson representation. And then I would study N bosons released from a deep trap and evolving in time. Doing that, you find out that you can get an analytic expression for it, and there are two different regimes that you can analyze. One regime is if you put it with periodic boundary condition, but you don't fill all the levels. And again, the effect, the system can expand into those open spaces, leads to a different behavior than, well, I would explain that, when it has a fully occupied situation where it cannot expand. So since I'm running over time, I will just make one comment, which I think is very cute. We can do it for attractive and repulsive interaction. When the interaction in particular is attractive, namely C is negative, then the eigenstates are described by what is called strings, which are bound states, in which case the work probability consists of two parts. One part which has unbound momenta, the other part which has bound momenta. The unbound momenta is pretty standard. It's obtained by taking the case of unbound and C flipping to minus C. That is what is called a Super-Tong-Girardot experiment, where you flip suddenly the coupling constant from repulsive to attractive. But what is even more interesting is the bound state contribution due to the strings, which allows a new effect to appear. The bound states lower the energy, and you can extract non-vanishing work even for negative value of a W. Namely, if you can extract work, you have a non-zero probability that work can be extracted from the system. It looks as though it violates the second law of thermodynamics. It does not, because on the average, it's still positive. You can prove that using Dzerzhinsky theorem. So here, just one slide illustrating the situation where the bosons are not free to move, but are going from a mode to a superfluid. And again, you can do very detailed calculations. So here are the conclusions. Quenches in cold atom experiments, work distribution is measurable. You can calculate the effect of the quench on local correlation functions. You find R renormalization group, flow in time, dynamical fermionization. You can calculate work distribution for strongly interacting gapless or gapful system. And you can calculate universal edge exponents, which I didn't have time to explain, and long-time behavior of Loschmidt echo, all of which can be measured in the laboratory and compared to the analytic calculations. Thank you.
Thanks, Natan. So maybe I can start with the question.
Yeah, I'm sorry, I didn't measure time correctly.
Oh no, we've still got plenty of time for questions here. So
okay.
I'm trying to understand a little bit about the generality of this Judson representation.
Yes.
And so in this formula, you've got this contour integral of 1 over lambda I minus lambda j.
Yes.
That's very much special for the Lieb-Liniger model. Right?
That's
in
correct.
In other cases, you'll get a cosine.
Well, you have to know the eigenstates. And once you know the eigenstates and the S matrix, you can identify what is the appropriate Judson representation.
Okay, so this works even when it's more complicated.
Oh yeah. We did it for a different number. We did it for the Hubbard model. We did it for the XXZ model. So it's quite a number of models you can do that. It's just a question of work, but there exists one for each.
Other questions? I actually have another question while people are thinking. So this technique is, in some sense, it's a way of getting around having to calculate form factor.
Exactly.
But this shows up in other contexts, not just non-equilibrium, right? So for example, if I were to take a beta ansatz model and add a perturbation and try and do perturbation theory, you also end up with a bunch of form factors. Could this technique help with those sorts of calculations? Or?
I mentioned, I haven't tried that, but probably it could be used also in static situation, but yeah, I've not done that.
Other questions? Okay, if not, it's time for us to move on to the next speaker. So let's thank Natan again.
Thank you.